Relative entropy is non-negative, another approach. So suppose PZ and QZ are strict positive distributions, no zero probability mass at any z. Let SP and SQ denote their alphabets respectively, as we have done before. Then if the sum, which is the relative entropy, is equal to 0, then the two distribution must be the same. So if the sum is equal to 0, the sum is equal to 0, then it has to be that the two distribution should be the same. Okay, this can be seen also from this proof. So proof here is that the relative entropy P and Q, by definition, is lower bounded by this expression right here. So what I have done, so basically in this case, I have this argument replaced with 1 minus Q over P. So log of an argument is replaced by 1 minus of inverse argument. So that's what it is. So we can take a little closer look, and we can say that log of x, and then here 1 minus 1 over x. Okay, that is what we are doing. And this one says this one is greater than or equal to, left hand side is greater than or equal to right hand side. And then is this true? When do we have the equality? And then this is true when you draw the two functions. So this is log of x, and 1 minus, so this is 1 over x, and then you invert it, then this is the inverted 1 over x, and then if you move it up by 1, move it up by 1, this is the 1 minus 1 over x. Okay, so that's that. So the two functions that we are comparing should come out. Let me draw it one more time, clear way. So here is x-axis. This is 1, 0 here, and that one. Another one goes like that. So that's 1 minus 1 over x. This is log of x. At input 1, both will give you 0. So that's the case. So this inequality, the first inequality, makes sense because of this fact. Let me erase it. So that is the reason. And then the second one line is equality. Basically, you apply PZ to the parentheses, then it is PZ minus QZ. And if we separate them, it came out this. And this one is always 1 because this is the summation over the whole alphabet. This may not be equal to 1. So because SP is not the alphabet of QZ. So SP is not equal to SQ in general. So in such a case, this summation is not over the whole alphabet set. So this may not be equal to 1. So it is in general smaller than 1. So 1 minus a number smaller than 1, then basically this is low bounded by to the case that both of them are 1. When the both of them are 1, basically SP is equal to SQ. So now if we enforce the left hand side is equal to 0, the upper part is squeezing down to 0. So both here is 0 and this one is 0. That means the two sets must be the same. Okay, and this equality must hold as well. And this equality holds only if these 2 points are. I'm going to take this one in front, which is this one now, and then combine the two. So when I combine the two, it is log ux over px. Okay, I think I have some leftovers. So this one should be that. So because of this part. So there are some typos. Okay, sorry about that. Once I have done that, basically the first part is log of size of the alphabet. Why? Ux is uniform on X. That is the reason. And then this second part is nothing but negative relative entropy. Note that this is Ux at the top, Px at the bottom. So this is negative relative entropy between P and U. Okay, so having said that, this one here is a number, positive number, and this one here is non-negative number. So from a positive number, you are taking away non-negative number. So this one is the maximum at log of size of the alphabet. Okay. So when do you achieve maximum, which is the equality right here? That is the case when P is equal to U. So when P is equal to U, this part, the second part is 0, and then you attain the maximum. So entropy is maximum when the distribution is uniform distribution. Okay, once you have proven, you can use these statements as a fact. Unless you are asked to prove this statement, you can use these proven statements as fact. Now I want to move on to mutual information. Mutual information is given by this expression. So the mutual information between x and y is defined to be this expression. And then when I take a look at the expression, joint distribution I see, and the log of joint distribution divided by product distribution, px, py. So this is a relative entropy between joint distribution and product distribution. So it is a distance between joint and the product distribution. So we may say this way, relative entropy between joint and product distribution. So the mutual information I, x and y is non-negative. Okay, so this one with respect to x and y is the expectation of this log of ratio. So log of joint distribution over product distribution. So this one here is a random variable, since x and y are random variables. And the product assignments are random variables. And ratio of random variables are random variable. And then log of random variable is a random variable. So you can take the expectation. So that's the mutual information. So mutual information is relative entropy between joint and product distribution. Since it is a relative entropy, it is non-negative. So it is low bounded by 0. When it is not equal to 0, it is a positive number. So this one is based on the definition that we have given. And we start off with the definition, and then using the joint distribution, which can be written as marginal times conditional on y. So this one is conditioned on y, and then joint distribution can be written this way. And from the top and bottom, we can cancel py. Then we can say that this is log of p of x given y minus log of px. Then we take this into account, distribute into this parentheses. Then the first part is negative conditional entropy x given y. By definition of conditional entropy, and then minus log px, that part with together with this part is entropy of x. What happened to y? Basically, if you take the summation over all y, this becomes p of y, p of x. So that is giving rise to entropy on x. So I, x and y mutual information X and Y is equal to entropy on X minus entropy on X given Y. This is based on conditioning on Y right here. So we can cancel the PY. But we could have done conditioning on X. In such a case, this becomes Px times Py given X. In such a case, Px will be cancelled, and then the conditional distribution will be Py given X, which will give you Hy given X. And this part right here, P of Y will give rise to entropy on Y. So that can also be written as entropy of Y minus entropy of Y given X. Okay, so mutual information between X and Y can be written both ways, either H of X minus H of X given Y, or H of Y minus H of Y given X. So this one tells you how much one can tell about X, according to this, knowing Y. Why? Because this is the uncertainty on X. This is the uncertainty on X given Y. So given Y, there are still this much uncertainty left. So this mutual information tells you given Y, how much information, because you are removing the uncertainty on X by knowing Y, that means, this one means that how much one can tell about random variable X, how much information that is left on X knowing Y. So that is the notion of mutual information. Okay, so another thing is that if you switch the order, it doesn't change. So the equality stays the same.